I think we're a little bit behind the schedule right now. Just a little tiny bit behind schedule. But I will try and take us home on time. We're supposed to be getting home at, I think leaving here around 5:20. So it's, this was supposed to be an hour and a half, but
Now it's half an hour only.
now it's half an hour. But here's the thing. I think the most valuable thing to get out of this is a discussion, questions that you have. So I know that this is late in the day and we're all tired, but ask questions. It'll make this whole thing go by faster for you and me as well. I'm gonna go through a couple slides introducing BQSKit, what it is, and how you can use it, how it works. And then we're gonna jump into a Jupyter Notebook session, which I'll have links to at the end of this slide. You're welcome to join along. In the first 15 minutes of the Jupyter Notebooks is the most important thing. And here's something that's really cool. All of this stuff is online. We have a GitHub, and again, I'll have links to that. So all I need to do is get you hooked, and then you can go home and follow them on your own, and then ask me questions asynchronously if you want. Yes.
Really quick, are they gonna be here tomorrow?
Yes.
Okay, because
And yes, a
you
good
have
point.
people who came just for this tutorial for you, and then, so they will do their homework tonight and then come tomorrow.
Perfect. Yeah, I will be here. I'll be here tomorrow. So maybe we'll go a little bit over clock. If there's good discussion, we'll go a little bit over. Yeah, let's get started. So a little bit of background about myself. I'm Ed. Enough background. So we're going to talk about BQSKit, the Berkeley Quantum Synthesis Toolkit, and how you can use it to compile resource-efficient programs. It's a quantum compiling software kit. So the little bit of motivation for the entire thing is that, and even though the slide's a little bit old, the point is still very relevant. Quantum hardware research and development is experiencing a boom and has been and will be, which is an awesome thing. There's all sorts of new diverse hardware. Comes with new architectures, new gates. For us, on the software side, it comes with new constraints. This is a little bit of a burden, a little bit of an annoyance sometimes because everything's always changing and we have to always constantly be designing new software. But that's our goal, that's our job.
And there was a question in the chat. You're going to put the GitHub link up soon.
Yes, so there will be links here. It is github.com/BQSKit. So if you want to type that in. Yeah, and BQSKit's BQSKit, contrary to how it sounds. But yeah, so there's a lot of different hardware, and this is a great thing. There's a lot of cool things that are coming from this, but in the software side of things and the compiler side of things, we got to figure out how to take advantage of this and build compilers and software stacks that are portable. Compilation means a bunch of different things. We're going to be focusing on circuit transpilation, which is this concept of taking in a quantum circuit as a program, transpiling it to a quantum circuit that is maybe closer to being executable on a hardware. So we have the Berkeley Quantum Synthesis Toolkit, the powerful and portable quantum compiler framework. It gracefully handles every gate set and architecture, specialized pipelines for widely used chips. There are new pipelines that are coming out soon, and we're constantly developing and improving what we have so far. Generates resource-efficient circuits according to a wide variety of resources, whatever you care about the most. Handles error mitigation, and it enables, this is the most important part from a scientific perspective, is it enables effective algorithm and hardware design exploration. We have some really cool accolades, and we have users all across the world, both in academia and in industry. Here's a link. There'll be this link, the same link again at the end. Our website, bqskit.lbl.gov, is a launching point to everything BQSKit, as our publications, our GitHub page, our documentation, which is a good place to start and look at everything. All of our source code and everything is online, so you can get there and look through everything yourself. It's turnkey, so it's on PyPy. If you wanted to do pip install BQSKit, it's a Python package. That's how you install it. And it supports Python 3.8 and above on Windows, Mac, and Linux, so there you go. How it works is if you're using it off the shelf, which is one way to use it, you can do import BQSKit, BQSKit.compile, you put in a circuit, you get out a circuit. What goes in is anything that you have. What comes out is anything that you want. More specifically, what goes in is really any gate set, any architecture, qubits, qudits, states, many states. You can do unitaries in there. And we're always increasing the portability and what we can handle as an input. And what comes out is exactly what you want. Yep. By the way, if you have any questions at all, please interrupt, just shout out, cut me off. That's the best way. Yeah.
Yeah, so the first question, and maybe your next slide will answer this, but so the IBM, says the BQSKit compiler is the best ever. You don't need anything else. I think it says their compiler is the best ever. You don't need anything else.
And we're the best.
I have,
Why do we need another one?
I have something to say about that tomorrow, so please come to my talk.
I think,
Answer.
I think that it's a very important question, and I think it's worth a good response. I think they're all good compilers. I think BQSKit, Ticket, and BSkit are all amazing compilers, among others in the field. And they all do things a little bit differently and are not mutually exclusive. If you really are going to be running a end-to-end problem and you're pushing quantum advantage or whatever you're doing, and you really want to run a serious experiment, I, even as a BSkit developer, recommend you run all of them in a loop because they do different things and they can find different optimizations. Our claim to fame is portability, right? And we can handle any gate set, we can transpile to any gate set, which is something that the others have a little bit more difficulty doing. And we can find some optimizations because we work more at the numerical level, and I'll show that in a bit here. But all great compilers, all do great things. Of course, we all say we're the best. Clearly, we're the best. And you'll see that soon in a little bit. But working together is really where everything goes in the long run.
I had a question.
Yes, sorry.
So in this two-liner program that you have, where do you input the gate set?
It's not there, it's implicit, but what you want to do is you put a comma, and you'll see this here in a second. This is the tutorial, we'll go deep into this. You put a comma, and then the second parameter to the compile function is the machine model. And the machine model is your machine. And your machine is the gate set, the qubits, the coupling, all that fun stuff. We'll get to this in the hands-on. But yeah, and so that's where you tell it the machine you're compiling towards, and then the circuit comes out, is executable on that machine. And there's a bunch of other parameters. Any other questions? I promise, just cut me off as I'm talking. That's the best way to go. We'll keep us all awake. Parameterized circuit instantiation. So I've said it a bunch. We're very portable. We handle every gate set. This is exactly how we do it. We treat everything as a numerical function that we optimize. The way this works is we start with a parameterized circuit, and we're tasked with finding values for the parameters that minimize some cost function. Most typically, this is finding the maximum overlap with a target unitary matrix, but it can be really anything else. And because we treat everything here just as a numerical object, anything that you can represent in the quantum world as a numerical object, which is, spoiler alert, everything, it works with that. So that's qubits, qdits, any gate set, and we'll see that here in a little bit as well. Question?
Can you handle Q modes?
Q modes? You can handle
Can you
truncated.
handle Q modes?
So Q modes are qdits with infinite dimensions. We can handle truncated Q modes, so qdits. There are specialized compilation pipelines for Q modes. But this stuff on its own is a little bit more difficult to do things like that. But if you can build a cost function for it, we can work with it.
Something like that.
Yeah.
In the previous slide, your cost function, what is exactly that you're trying to minimize, optimize?
We want to make in this one as it is, right? And this is, you can substitute here. This one is, we want to make the final circuit as close to some target unitary as possible. Make the whole thing implement some target unitary as much as possible.
Your metric is like the lead-in distance between the matrix and the target matrix and the generated matrix, or what?
Hilbert-Schmidt distance between.
Yeah.
So that's you can substitute different things out. Okay, so why is this really powerful? In the compilation world is because we can take an instantiated circuit and separate out the function from the structure. The function is, what does the circuit do? The unitary it implements, the mathematical equation, the physics, the Hamiltonian. From the structure of it, the structure is how does it do that? The types and placement of the gates in the circuit. What we can do is vary one or the other, and in some special cases both, and then use instantiation as a tool to bring them back together along some axis that gets us closer to a goal that we have. And we can build algorithms this way.
We're gonna have a question.
Yes.
So if you say you are minimizing the distance between the unitary and the target unitary, does it mean that you can only handle a small amount of qubits? So if I give you like a circuit on 100 qubits.
If you give me a circuit on 100 qubits, BSkit can handle it. And you'll see in a second why. Synthesis and instantiation is a tool that we use in our compilation pipelines, but it's not the way we do everything. So I'll show you that there's a slide exactly on that. It's a very good question.
Maybe a variation on the theme. What if you get a very big matrix, which is a unitary, and you say, I have this matrix, if somebody divided it, and I want that to break down into my.
So-
What is the limit of the matrix size?
We have synthesis algorithms in BQSKit right now that handle up to around 12 qubits. We are currently developing a new method that will scale up to what you can handle in memory. So as long as the matrix can be handled in memory, we'll be able to handle it. That's coming out soon. Right now it's about 12 qubits, right? Most typically though, that is not the problem that we encounter, right? This is a pretty rare one for people to say, I have this 12 qubit one, but it does occur every once in a while. And we are building a good solution for that. And there's always QSD as well. So you can do like quantum channel decomposition or block CX to decompose these unitaries into smaller ones and then use our tools. Okay,
And question, the next update is gonna handle how many qubits you're going to?
as much as you can handle in memory. So if you can have the unitary on your laptop, you can do it.
So you said right now it's 12.
About 12, yeah.
In our testing, we're able to do it up to 8 and everything. Just
Depends on the matrix sometimes. Depends on how you set it up, depends on how specialized it is, depends on the hardware.
the new update is gonna be open.
Okay, so what can we do with instantiation? The very first place we started with is synthesis. That's where we get the name Berkeley Quantum Synthesis Toolkit from. Here what I mean by synthesis is the taking of a function, in this case a unitary matrix, something that represents what we want to do, and finding a circuit or a program that implements that unitary. And we do this in a bottom-up fashion, which is a very simple paradigm where we just start with an initial circuit structure, initial circuit template, and then we instantiate it. If that's a solution, great, we're done. It doesn't always work out that easy. So what we do is we extend the circuit template, we add a few more gates, and we reinstantiate and repeat this loop until we find a solution. How you extend the circuit, how you instantiate, how you take your first initial guess defines an algorithm that's bottom-up. And we have many different ones that do this. But one thing that we realize is we can take this paradigm and change it a little bit. And instead of starting with an initial circuit template and building it up, we can start with an initial circuit and make transformations to that circuit, whether it's changing the gate set or optimizing it. I'll show an example here in a second, and then keep repeating this process until we no longer can or no longer want to. And that's a way to optimize or transform a circuit. So we have two pipelines here, one to synthesize and build up circuits, one to change them. And both of them have instantiation at the center. So let's take a look at a concrete example here, gate deletion. Gate deletion is the process of deleting a gate. Let's start with the top left circuit. Go to the right, and by going to the right, we're just gonna pick a gate and remove it. Now that's illegal. You really can't do that in practice in general. But what we can do is use instantiation to reinstantiate the parameters to the remaining gates in an attempt to accommodate that lost gate. Doesn't always work, so you have to have the ability to reject and go back to where you started. But it works in a surprising number of cases. And you're able to take suboptimal circuits and optimize them very rapidly. And if you notice here that I don't have any names on these gates, maybe they look like C-naughts, but maybe they're not. Maybe they're Q-trick gates. It really doesn't matter here because, like I said, everything about this is using numerical instantiation and as a result, portable. You can handle Q-dits, Q-trits, you can handle any type of gate that you want. You can handle hardware architecture constraints as well. Very flexible in that regard. It's also very effective due to this concept of global transformations. You notice here that the entire circuit is changing to accommodate that lost gate, right? When you apply peephole or rule-based optimizations, you're looking at a very small subsection of the circuit, where with this, we're allowing the entire circuit to change. As a result, we can find very non-intuitive optimizations this way.
How does the cost scale in the number of qubits?
Exponentially. Like classical runtime? Yeah, exponentially. So in a couple slides, I'll show you how we kind of overcome that challenge. So we have a bunch of algorithms. This is the good slide here. The way we overcome the scaling challenges that are imposed by instantiation-based algorithms is through partitioning. So if we have a very big circuit, million qubits, and we have a million billion blocks on it, what we can do is we can partition the gates in that circuit by grouping together adjacent gates into blocks of, say, a fixed width. In this example, we're taking a 5-qubit circuit and forming three 3-qubit blocks in that circuit. Then we can recurse, apply our algorithms to these blocks, and then piece everything back together. And that's how we overcome this. This restricts the global view that I just mentioned as a very powerful tool of instantiation. So it introduces a trade-off that as we increase the block size, we get better quality of results. As we decrease the block size, we get faster results. One cool thing about this creates an extremely parallel workflow. This is all push button in BQSKit. So if you have a million billion blocks, but you have a supercomputer with a million billion nodes, you can send a block in the compilation algorithm to each node and run it, get them back real quick in no time at all. And BQSKit has push button Slurm script, copy and paste Slurm script for running this stuff distributed on Perlmutter, and you can easily adapt that to other kinds of systems as well.
The question.
Yes.
Do you support dynamic circuits or mid-circuit measurements, that kind of stuff?
Yes, we do.
So if you optimize each block independently, how do you know that you're optimizing the whole circuit globally? What if like by tweaking one block, you're actually making it worse for another block?
You don't. So, okay, that's a very good question in the sense that it's hard to track real errors through a circuit. But what we can track is that this block has, when I compile this block, I know the exact error on it, right? So I can actually compile this block to say perfect, 0 error, or to 10 to the minus 10. And then you can actually, put the slide here. What you can do is you can add up the errors of all of the blocks as you compile them, right? And this is the approximate logical error, right? So this is during compilation, it's not real error. And that gives you an upper bound on the error, right? Which is, it's not a good upper bound, but it's good enough for us to make conclusions that our transformation was valid. That the optimization or the transformation that we performed did something that is acceptable, that we're happy with. In terms of, is it something that we wanted? Well, that's maybe C not count, or did it make it closer to being executable on the hardware? Things like that. Does that answer your question? In terms of watching like real error dynamics through a circuit, that's a fun question to pose. Yeah.
So I noted that you had cited like Ryan's paper over there. So Ryan Wu's paper. So I have a question because of that. So you're talking about the error, like you can specify some error, and when you're doing your in each block when you're changing stuff, so you want it to be within this error budget, right? So do you really see like a smooth gradient for this error? Because in my experience, like you can achieve like error like 10 to the power minus 10, but if I set it like 10 to the power minus 5, it doesn't, in some sense, it goes back to 10 to the power minus 10, right? So is it now better in terms of like achieving like arbitrary error thresholds?
So this has to do with the fact that we're walking a discrete space, right? Like you can only add one extra gate. So one minus gate might be 10 to the minus 3. One more gate might be 10 to the minus 10. And there is no in between, right? That's just the way it is, especially when you have small circuits that you're optimizing. Like think a 3-qubit block, there really is the granularity that each gate adds is pretty coarse in terms of how it affects the error, especially as you get closer to 0 error. In terms of the big block, though, it's important to watch this upper bound error to make sure that we're not doing something that's invalid. But there are approximation methods too that we can do a little bit more fun stuff there.
So here is a couple of questions. Is there a way to verify this and validate this between after you do these approximations and then all these errors and then make sure that like at least quantify all of that? And then the second question is, you're summing all the errors. Who said that it's linearly additive?
So there's a proof for this.
There is.
There's a proof for this. Yeah.
It's the upper bound, that's an upper bound. The actual error.
Yeah,
is not
the upper bound. So
It's a very bad upper.
It's a very bad upper bound.
Very, very bad upper bound.
yeah.
That's why there's a proof. I mean,
You're giving me the worst case scenario of the errors that they cause.
Yes.
Okay, that's proof. That proves it to be.
Yeah, so there's a proof for this, but yeah, it's
But for validating or verifying, that's a different story. I want to verify that what you did is good enough versus the original one that I started with, right? Or even better.
why? So if I give you the upper bound and the upper bound's 10 to the minus
The
15.
original circuit that I gave you and the circuit that you gave.
Yeah.
I want to compare the two.
Yeah.
So
The upper bound is 10 to the minus 15, so you know that the difference between them is at most 10 to the minus 15.
The thing is like, I mean,
if you know sum over epsilon I to be 10 to the minus 15, your actual error might be 10 to the minus 20. Like much smaller, but like you always know that is much smaller than 10 to the minus 15. That's right?
Yeah, that's exactly right, yeah.
Let's say you start with,
It's a bad upper bound, so I want to see where I am.
But the error bound
That's-
will give you the maximum error you could get and more. So your error will always be better than this value.
Yeah.
You're guaranteed to be better than whatever it is.
What you can do is,
Set a lower bound
Yes.
and then iteratively keep trying, right?
you can, so as this block size scales to the size of the circuit, the upper bound scales to, in the limit, becomes the actual error, right? So you can make this block bigger. And the size of the block that you're verifying on doesn't actually have to be the size of the block that you're doing the compilation on. And so this is how it is in BQSKit. There's two levels of partitioning, one for the error verification and one for the actual compilation. We do the error verification with much larger blocks, because that's as simple as just checking, the unitary is correct or not. And that's something that we can do with very large blocks. So we get, accurate enough upper bounds, and we're able to verify all the transformations that we've done that way with very much, a lot of confidence.
Sorry, maybe I missed it, but if you have a lot of qubits such that you cannot store the whole unitary in memory, what is the loss function, or like what exactly are you trying to optimize?
So you can't do, at least with our methods, we can't do anything that way, right? So this is like, you're going into like sketch territory and other types of fun stuff. This is what we're doing. So, okay, there's two stages here, right? There's the direct synthesis stuff or direct instantiation, where you're solving this problem. This requires full unitary, dense unitary mathematics. But then once we go into the compilation part of things where we're using that as a tool, what we do is we take a very big circuit. This could be millions of qubits. I mean, and I think we've done like tens of thousands of qubits now, and the limiting factor there has just been that we don't have good circuits to test on. Not that we can't go further. But what you do is you partition them, and then you run those algorithms on the blocks themselves.
Plus, I'm confused about what is the goal for each block? What is the target unitary for each block, and how do we know this target?
I calculate it. I can multiply these gates together to calculate the original input unitary. So this block originally was, say, U. I do some transformation, now it's U dagger, or not dagger, U prime.
And what are you trying to bring this U most to like which unitary?
The original one. So, okay, here's the like, what happens if this was 20 C naughts, and now I found a new type of circuit that was 10 C naughts that implements the same unitary.
Oh, I see.
And I put it back. So now the whole thing I do that for every block. Now it has,
So the goal, so am I understanding this correctly, that the goal is to implement the same unitary, but using, for example, less amount of gates?
For most of the workflows that we have, yes. That leads us into the next slide. These questions are awesome. They're keeping us going. So to build on this, what the goal is really dependent on what the workflow is. What the workflow is, let me define that first. This is the thing of putting all of the pieces that I've gone over so far together to solve an end user task, right? So optimization is what we just described, this optimization one. We have many different ways of doing that, where the goal is to take the original block and find another, circuit that implements that original block with fewer gates, fewer whatever, if you care more about C naughts or if you care about total gates. But we can also do mapping and routing. And in that case, it's not necessarily fewer gates, but it's more that it matches the hardware better or requires fewer swaps, right? We can also do approximations, where now we're actually really concerned about the actual error that we're going into and how we build multiple of those and how the errors are biased to one another. We also have gate set retargeting and circuit resizing. I have a couple cool results here that's saying, look, we're the best one out there. And that we can do approximations, and these approximations actually give you close to the ground truth, better than actually, you can do high error compilation many times, and then do something with the results to aggregate them and get better results than one really good compilation. All of this, I have to acknowledge, has been a multi-institutional team. A huge effort from many different people, and it's been awesome working with everybody here as well as others. All of this couldn't have been done without NERSC and the support that we've gotten, and the Perlmutter and all of the resources that we have here at LBNL. So I have to say thank you to everybody involved. Okay, how are we doing on time? Bad. Okay, so here's the QR code to the BQSKit tutorial. The link is right there if you want to just type it in, github.com/BQSKit tutorial. With what remaining time we have, I encourage you to follow along. I'm definitely gonna to go through it a little bit quicker, but the questions are awesome. It's great that we're having such a lively discussion even at the end of the day. That's more important than anything that I can just lecture on the tutorial, but give everybody a couple more minutes, just kind of get set up here. And I'll switch over here in a second. If there's any questions or any uncertainties that you want to go over, it's a good time.
So how big are the blocks at which you're doing the optimization? Like what is the like a good size?
It depends on the algorithm that you're performing. Like if you're doing PAM, 3 qubits is good. If you're doing optimization with gate deletion with the Q factor sample algorithm from Milan, we can do up to, I think, what, 12, 13 qubits?
I would do 10, 12, it's like a really, really long time.
We can do 10, and that's using like GPUs and, we have, it depends on the algorithm. But like for mapping 3 qubits with the PAM method is really good, but it depends. But yeah, somewhere in that range.
Yeah, I'm just wondering if I could go to like, if it was like 2, 3 qubits, for example, whether I could just optimize at the pulse level and therefore I can actually like, so earlier you were mentioning when you delete one gate, the error it adds is too high, right? But if I'm working at the pulse, maybe I can optimize at a finer granularity or something.
You're talking about like pulse optimization, that kind of stuff.
Yeah.
So that's there's I think ways that you can combine this partitioning approach with optimal control and do that, similar to that. So that's a very interesting idea. That's not one that we've actively explored, but very interesting.
Are you actually using this to target any existing architectures? Just wondering about the connectivity issues, right? If I have some sort of oddball connectivity layout, how well does it actually transform the circuit and do all the swapping needed?
We're the best. No, okay, so honest answer, it does really well. So actually mapping is I think one of our strongest suits in terms of overall workflows. Because of this permutation aware mapping PAM thing, we can consider permutations of the blocks. And we have a way of resolving permutations in that. We do use it. You're asking me if I use this tool, I use it every day. With everybody that I work with, I encourage them to use it as much as possible. And it's sometimes it gives you neck and neck results with other tools. Sometimes it gives you completely unintuitive results. It's not unfamiliar for me to be working with a domain expert and them tell me that there's no way that you can do better on this circuit. Just this is the most optimal way to do it, and then we do better. But that's because we also, everything that we do is numerical, and we introduce slight errors in everything that we do, and we control that, but that slight error usually allows us to get an advantage in gate count. Yes.
So is there a way to have like a don't touch gate in each of these blocks, or like or to like leave in parameters? So I'm just thinking about like from the VQA perspective, where if I was trying to like optimize an ansatz, but I still want all my tunable things to remain.
Yes.
Oh, there is, okay.
Barriers.
Yeah, so we have barrier support, and we have there's this thing called a frozen parameter gate. It's a composed gate. You plug another gate in, and you can say freeze these parameters in that other gate, and then it's like a constant thing.
Okay.
Yeah. So honest question, and 0 is a totally fine answer here. Who's here is going to actively follow along? Raise your hand. Okay, that's awesome. Okay, great. Let's go through this. Okay, that's so this is the first module of 3. We're not going to go in the other 2 today because those are each like their own hour-and-a-half thing. This one is really an introduction to BQSKit. It's broken down into 3 sections. In the first section, we're just going to introduce kind of how to load a circuit, basic stuff. We'll go through it pretty quickly. The second section is the main section where we talk about how do you actually do the compilation. And the third section is looking at the parameters, how to fine tune it, what they mean. Okay, so let me go ahead and restart and clear everything. I kind of cheated earlier. So we have some circuits inside of the tutorial notebook, but I encourage you to plug your own in and run with your own circuits that you're interested in compiling, because that makes it more interesting as we go through. So let's go ahead and run this. You can load a circuit by importing the circuit object and doing circuit from file. It supports CASM right now. You can also load in circuits from BQSKit, QTIP, Circ, PyTicket. They have different names for the functions. Here in this example, it's just BQSKit, but you can swap out BQSKit for one of the other ones. So in this example, I'm going to build a BQSKit circuit and then just use BQSKit to BSKIT to convert it to BSKIT. One thing to note about this is that all of this stuff goes through CASM anyway. So if you have gates in there that have trouble being represented in CASM, just keep in mind that that might cause issues, or it might be decomposed to CASM or done some decomposition before it gets translated.
CASM 3 or CASM?
CASM 2. There's a couple ways to get some information about a circuit. So we have circuit.gateCount. So it prints out just a nice dictionary of all the different types of gates in the circuit. This is for that Heisenberg circuit and how many there are. We can also look at the logical connectivity of the circuit. So this is what is required of the hardware as the circuit is right now. And these are basically, you see 6, 7 here. That means that there is at least one gate between qubit 6 and qubit 7 in that gate, or in that circuit. So if we want to compile, remember from the slides, BSKIT.compile. So it's not BSKIT.compile here, I did from BSKIT import compile, but same difference. And you'll see that instead of, I think it was 360 CNOTs, now we have 338. So we optimized it some bit. You'll also notice that the U3 gates, or sorry, all the single qubit gates have become U3 gates. And that's because the default configuration for BSKIT is to compile to CNOTs and U3s. And we didn't change anything about the logical connectivity, most likely.
You didn't have already a logical connectivity structure?
Yeah. Every circuit has a logical connectivity because this is just, what is required of the circuit or from the hardware from the circuit.
Not the full.
Yeah.
So like when you're compiling right now, does it do block by block? And then if it is doing it that way, like what is the size of the block? Because we didn't set anything. What is the default for that?
3. It's doing so under the hood, it's doing a lot. It's not just doing one workflow, it's doing multiple workflows. In the second tutorial notebook, we're not going to go over that today, but if you're interested, look at it. There's a way you can actually get the workflow printed out, look at it, change it, add it. The second notebook is about doing a deep dive in an algorithm and modifying the workflow to fine tune it for a specific algorithm. So you can actually get that information, get the workflow and change it. Or you can just build a new workflow outright. Everything we do in BSKIT is with passes, and you can build your own by just making a list of passes. Okay, so we have optimization levels. We don't have optimization level 0 because there's no way that we don't do any optimization. So we have 1, 2, 3, but we also have 4. That's where PAM comes into play, and we can do really a lot. The difference in time between 1, 2, and 3, and 4 is not analog to a classical computer. It will grow quite significantly as you go up from 1, 2, 3 to 4. So keep that in mind, that if you're running 4 here on a laptop, it might take a good couple minutes, especially depending on how big your circuit is. But it's well worth it. Yes.
Is there a way to get a representation as a picture, what gates are there?
Unfortunately, not right now. Okay.
Yeah. I've been asking for this.
Yeah.
You keep receiving the same request.
Important to BSKIT.
You can port it to BSKIT. The downside to that is if you're working with custom gates, they might get there's some loss in transmission sometimes, but yeah, we'd be happy to take contributions in that regard. By the way, yeah, BSKIT is completely open source, so if you have an issue with it, which, if you have a bug, we encounter bugs from time to time. It's a very large program, very large software. Feel free to yell at me through the GitHub issues report. We really do welcome that, and we try and improve it as we go. And we do constantly monitor our GitHub page. Okay, last thing on this first section. If we want to save it out, you can do circuit.save, and you can write a CASM file, or if you want to go back to the framework that you came from, it's the reverse of what we started with. Any questions on the first section? Cool. I think this is Aspen M2 from Rigetti. I don't know if it's still in play anymore. I think they retired it. But this is a machine, the quantum machine that we want to target. So this is what a logical connect or a physical connectivity might look like. And so the question is, let's see how we can actually compile to this and be portable across different machine models. First thing we're going to explore is gate sets. So we have this library of gates called BQSKit.ir.gates. You can import all your gates. I think there's somewhere here, is maybe a couple more down, is a link to a web page with our documentation of all of our gates. In this example, what we're going to do is we're going to transpile to CZs, RZs, and SX, square root of X gates. And the way we do this is we build this machine model object. The machine model is a model of the machine that you're compiling towards. You don't have to specify everything. It'll have defaults if you don't want to specify things. But in this example, I'm going to say it has, the same number of qubits as my circuit, because why not? And then the gate set is the one that we want to compile towards. So in this case, it's CZs, RZs, and SX. And then when we compile, what we do is we pass in now a model parameter, which is the machine model we want to compile towards. Let's see what happens.
That's the question.
Yes.
So regarding the model, just I would like to remember, my students should know this better than me. But do you include also not only the topology or the connectivity between the qubits, do you include also the error levels for each of the qubits and then the link error between qubits, or just on the topology?
So topology is going to come up here in a bit. We now have a way to specify weights. It doesn't quite capture error, all the way, but you can specify weights on the links, and mapping will take advantage of that. Map around that.
Right now.
I mean, that'll be in one of these. I'll show you how to do that in here in a second. But you can't just like load in an error model or something. You have to build it yourself. Okay, so what we see here is that the circuit is now in the gate set that we asked it to be in. That's the portability of BQSKit. It's as simple as just saying here, these are my gates. Any questions? Let's look at another example. So in this case, I'm going to say ZZs. I think still RZs and SX, but ZZs. I just defined a little helper function here to just make it simple to say compile this to that gate set. And that's it. We now have ZZs. We really can get funky with this. I don't know RYY gates on any hardware. I know ZZs, I think XXs, but not RYYs. But why not compile to them? We see we get actually a better result. At 120 of them instead of 220 on the other ones. They're more expressive, that's why. But you can transpile to anything here.
ZZ is not, what do you mean by ZZ gate? Is it, it's not RZZ?
But this is RYY.
Oh, no, I was talking about like the before one. What is that?
So ZZ is RZZ pi over 4, or negative, or pi over 2. One of those.
ZZ, right?
ZZ. So it's not RZZ, but there is an RZZ. If you want RZZ, you put RZZ.
If you put RZZ, that would give you 120 as well, right?
Yeah, something like that. And then probably exactly 120. Then RYY is, yeah, RYY. It's just to point out here that it's as simple, if you want to change it to anything you want, it's not like we have special pipelines built for each gate set. You can plug whatever you want in here and it just works.
I'm gonna ask you an annoying question. What is the between ZZ gate and the control Z, like CZ? Like what is the difference between those two?
So ZZ is E to the I, ZZ. CZ is like a controlled Z. So it's like, 111 E to the I, whatever.
They're probably equivalent up to a global phase. That's what I was thinking. But anyway,
I think they are.
I think they are different.
They're
type of
up to
local
single
units.
qubit rotations, I think.
You have like some local Z rotations on the control Z, which you don't have in ZZ 5 or RZZ 5/4.
they're the same up to global phase, but like your cost function keeps track of.
Not up to global phase, up to single qubit.
You have the single qubit unit in which you have to multiply.
Let's talk more about this offline. Okay, so last one on gate set, you can do multiple entangling gates. So here I have, this was the Google gate set. Square root iswap, Sycamore, CZ gate. It'll figure out when to use which one. So we see some Sycamore, we see some square root iswap, we see some ZZ. So it compiles to multiple entangling gates as well. So there's an exercise here. define your own gate set, compile to it. Let's switch over to the solutions for time. To show some of the other interesting things that you can do with this. There's a solutions notebook also in this. It's kind of buried in one of the folders that says solutions, but. So, okay, one of the gates we have is called a polygate, and it parameterizes all of SU4. Well, in this case, SU4 because we said 2 qubits, but you can put whatever qubits you want in here. And you can see that this is really like, this is the most expressive 2 qubit gate, and we can compile it to 113 of them. So you can do some, really anything you want there. Because we're not doing any kind of optimization levels there, you get some single qubit gates as well, even though those really could all be merged. What we can also do is, from a hardware perspective, say you are, what is this one? You're trying to decide what is the gate set that you want to implement on your hardware. Maybe you know something about your Hamiltonian. In this case, maybe it's just fully random. So what I'm going to do here is I'm going to pick 10 random 2 qubit gates. I'm going to make them constant, and I'm going to compile to that. So this is really just 10 random 2 qubit gates. And then I'm going to figure out, I'm going to compile to them. And we see that it kind of ranges. Some of them are getting 250, some of them are getting 300. And this is a way that you can kind of do a little bit of hardware design exploration using this portable effective synthesis. Another way to do this is, in this example, we have an RXX. And the question is, what is the right, I can only calibrate one parameter. What's the right parameter to calibrate? I omitted pi and I went through a range of a bunch of them, and then I'm compiling to all of them. And we can see that there's some variance, not that much, but there's some variance in the resulting compilation results. And maybe from this, if we have, say, a class of algorithms that we care the most about, we can really fine tune our implementation of a gate for that set of algorithms or for our users. Any questions? Okay.
A question.
Yes.
So what about parameters? So if you have not constant angles, the parameters in there, does it retain all those? And
So the parameters, when you do the compilation, it assumes that every parameter is a variable that can be changed.
you're doing this after the parameters have been applied.
Well, like in terms of a variational algorithm, yes. So this is going to be on the like inside the loop of a variational algorithm. There are ways to do the compilation outside, like a partial compilation scheme where you do compilation around the parameters, put it back, and then maybe do some more compilation inside the loop with the parameters. There's also seeded synthesis. In one of the other notebooks, we have built a workflow for these kinds of variational approach where in between the iterations, we're actually using the results from previous compilation to seed the results of the next compilation, make them higher quality and faster, get the results faster. But yeah, you have to be a little careful around there. If you do want to freeze the parameters though, there's a gate called the frozen parameter gate where you can specifically freeze certain parameters, make them constant and not change. Okay. So, okay, let's talk about topology. It's not as different from gate set. In this case, I'm just going to say this is my coupling map. This is the connections that are allowed on my hardware. So qubit 0 can talk to qubit 1. This example is, I think, 2 8-qubit stars. So we have in this first star, qubit 0 can talk to 1 through 7. In the second one, qubit 8 can talk through 9 through 15. And then 0 can talk to 8. So these are 2 8-qubit stars connected. It's a very weird coupling graph, but nonetheless, we can compile to it just the same. So here I'm going to say I have 16 qubits. That's my model. I'm going to compile the circuit to that one. And what we see here is that I print out also the logical connectivity of the resulting circuit, and we see that it matches the topology of the coupling graph. We do see that the CNOT gate count goes up, but that's just how sadly mapping works. If we turn up the optimization level, we'll see that improve as we go. And if we go to optimization level 4 with permutation-aware mapping, there's a chance that actually might go down.
Is it possible to optimize our coupling graph without actually manually looping over it?
That's an interesting question. I'd love to talk more about it. Right now, off the top of my head, at the end of the day, all I can say is you have to optimize over the.
So I'll have to loop over it myself.
But that's a very interesting question.
And I mean, I've asked this because in some of the atomic architectures where you can move them, you might want to decide what the best configuration to get a particular circuit.
I see. So this is kind of like an initial layout question. There
Yeah,
are
so
ways
which
to
layout
do-
gives me the shortest circuit?
There are passes in BQSKit to do initial layout, guessing. And this is one
But
area.
it's not just the initial, it's also like every block will have a different layout. So I want to figure out what is the best layout for that block.
Let's talk about this more offline.
Yeah, let's do that.
Okay, and then here we go. We can check that the circuit is compatible. So there's on this function on the model, which is compatible to the output circuit. So I think that I made a promise and I broke that promise. I'm going to real quick go through the rest of this. I encourage everybody to, I hope I hooked everybody enough. Real quick, encourage everybody to go through it. We'll run through this, kind of show a little bit about what's possible. But even beyond this notebook, there's 2 more notebooks. And then there's some more that we're working on actually taking even deeper dives into specific algorithms with BQSKit as well. But yeah, so what else can we do? So go to the solution notebook first. So if you want to know with mapping, if you want to know how you mapped, you can get out the initial and the final mapping. Tells you exactly how to do that. There's a parameter to the compile function. It's very useful if you need that information. We have pre-built models. You can figure out which model, which hardware is the best for your specific algorithm by just looping over all of them. This is the distributed quantum stuff where now you can actually say in the coupling graph what the remote edges are. And if we say that these are remote edges, then the mapping algorithm will actually take that into account and try to use that as little as possible.
You have a weight there for that.
We have a weight there. You can actually set the weights too. There's some other parameters. If you look at the documentation, you'll see that. And this is an example where if we compiled it, looking at that link between 0 and 8, it was 51. In this case, with the distributed, when we set it to be distributed, it was 24. Under the hood, you can do synthesis. Synthesis is being done, but you can also just plug a unitary. So here I just say, here's my unitary, it's a Toffoli, I want to compile for it, I can compile for it. There is partitioning, we talked about this. The block size introduces a trade-off. You'll see here that if I set the block size to 4, this is the max synthesis size parameter. If I set that to 4, my gate counts go down. The quality of result goes up dramatically, but so does the runtime. If I set it to 2, the runtime goes down dramatically, but you'll see that the quality of result also goes down. All of this is approximate. We talked about the verification procedures, and there's a bunch of blurb explaining that in a little bit more detail, but what I did here is I created a situation that's going to return a high error circuit. So I set the epsilon, the synthesis epsilon to 0.5, meaning return success when the synthesis is 50% away, which is a horrible number. But then also print out an error. Tell me if the upper bound on the error was greater than 0. So it actually will print a warning. It'll calculate now the upper bound, and it'll say, hey, this upper bound on the error is greater than the threshold you had set. It's not going to do anything different other than just alert you saying, hey, this compilation, you might want to rerun, set some parameters differently, rethink it a little bit to make sure that you can bring that upper bound down a little bit. You can see it's a really bad compilation. We got an error of 1, as bad as you can be. In this case, we actually correct that. So we set our synthesis epsilon to 10 to the minus 3 now, which is by default, it's 8. And then we set our epsilon threshold to 5e to the minus 2. Maybe that's all we care about. We can get some improvement in the results that way sometimes. But sometimes, you don't really see that much of an improvement. It depends on what you can do in your algorithm. So there's an exercise here for you to verify some previous compilations. I'm going to skip over that. And then, so one thing to note here is that everything that we do in BQSKit has this thing called a runtime underneath it. This is how we run things in parallel and as efficiently as possible. This is built by a compiler object. So when you call compile, it under the hood builds a compiler object. And this takes a little bit of time, a couple seconds sometimes, depends on your computer, to spawn a bunch of threads. You can actually have this be distributed as well, but there's a Slurm script in the documentation and a guide for that. But one way you can speed up a compilation is if, say, you're doing many compilations, what you can do is instead of just looping over compile, what you can do is cache a compiler object and then pass that to compile. This way it only gets created once. That saves you really just thread spawn time. In this case, we're just synthesizing a bunch of single qubit unitaries. The actual time to synthesize a single qubit unitary is like microseconds. So all of this time that you see here is really just all of the extra fluff in starting threads and things like that. When we synthesize 3 in a loop, it takes 5.5 seconds. But if we cache the compiler object, then we save a good amount of time. And that's it.
Question. Whole thing just written in Python on the surface, or is there any optimization?
So there's, we have Rust. We have a BQSKit RS package, which is a separate package that BQSKit uses to do some accelerated, the really core parts of the compilation, the instantiation, the optimization. And this is where we see the importance of having it written in the lower.